Good afternoon. Last time we talked about herbicide selectivity, and we covered the phase 1 reactions. Now we want to proceed to phase 2 reactions. So our topic is herbicide selectivity. So it's herbicide. Okay, sorry about that. Select the pen. Let me select the pen. Right. So it's herbicide right? Selectivity. This is what we covered last time. Wait a bit. Let me adjust my slides. Starting. Sorry about this. Let me go to slide number 1. Okay, here we are. Let me pick the pen. Right. So the topic is herbicide selectivity. Let me just write my name here. Right. So we wanted to start with the phase 2. What we should notice that the herbicide metabolites carrying the following functional groups, that is the OH hydroxyl, the COOH carboxylic acid, and NH2 in brackets amine. Will undergo further reactions. Now these reactions which are taking place in the phase 2 are known as conjugation reactions. So let us put this title: conjugation reactions. Now, these reactions require the following agents. These conjugation reactions require the following agents. I don't know that is the correct term. Right? The first one is number 1, glutathione. Yeah, glutathione. Number 2, we have glucose. Number 3, we have got aspartate. So what we are going to do is to explain how each of those agents play a role, how they play their role in changing herbicide metabolites. So we are going to start with the glutathione activity in the cells. So let me pick the pen again. Glutathione activity, glutathione. Okay, sorry about that. Hello. Sogamka, yes, yeah. Uyayirapoko. Ndeweningi izviyo rapo. Mapfunde. Yes. Yes. Runoita. Yeah, this is right. Zviyo, ndewe zviyo. We brown ga. Irapoko, rapoko. Kana kuti finger millet. All right, ga. Sorry about that. Call. Let me continue. I was about to write about glutathione. Yes, I still have my pen. So, glutathione. So, glutathione is very important in removing herbicide toxicity. So, what is glutathione? What is glutathione? It is a protein which is made up of 3 amino acids. That is glutamate, which you can write in short like this. Then sustain. Which you can just say cis in brackets. And finally, we have glycine. Which we can represent like GLY. So please note that this one, glutamate, cysteine, and glycine. They form glutathione. I hope I am not messing up with these slides. Still on glutathione, so it's made up of this glutamate, glue joined to cis, cysteine, then joined to glycine. It is important to note that here we have an SH. If I could change the color a bit. This one here is the reacting component of glutamate. So it is the SH or sulfur bond or sulfur part which allows glutathione to react with a herbicide metabolite. Now let us move on to talk about the herbicide metabolite. Herbicide metabolite this is the herbicide which has been altered in phase 1 by cytochrome P450. So this herbicide is likely to carry this radical, the OH. So this is our herbicide. So what is going to happen is that glutathione is going to combine with this herbicide radical in a conjugation reaction. Conjugation reaction. Conjugation reaction. So we'll have our herbicide like this plus glutamate, cysteine with our SH here, and glycine at the end. The product, if we show with an arrow, will be like this. Okay, let me use an eraser. So the product is going to be like this. Glutamate joined to cysteine, then to glycine. Here we now have S joined to the herbicide. This is now glutamate. It is now glutathione. Sorry, glutathione conjugate. Now, the glutathione conjugate will cease to be toxic. Let me clearly separate this. This is the product which we obtain. This is less toxic. Glutathione conjugate. This is less toxic to the plant. Please note that maize leaves contain a lot of glutathione. And this is why atrazine is tolerated by maize plants. However, we do have some lines which, depending on the amount of glutathione they contain within the leaves, we may have some breeding lines being affected by atrazine. But in phase 1, atrazine will carry an OH which is suitable for combination with the glutathione. Yeah, so we have glutathione conjugate here, which makes the herbicide less toxic. Now, we can move on to say that what really catalyzes this reaction, the conjugation reaction. We need this enzyme it is known as glutathione S transferase. It catalyzes the conjugation reactions. Please note sometimes glutathione combines with atrazine at the chlorine atom position. At the chlorine atom position. So OH may not be necessary. Okay. So I think we've just done the glutathione activity. I think what I should say that at the end, the glutathione conjugates where do they go, these glutathione conjugates? They will enter the cell vacuole. they will enter the cell vacuole. This is where they are stored. Stored safely. They will not harm the plant. The plants, if you want to call them. So this is it on a glutathione activity. You should understand that it goes for the OH radical. So we move on to the role played by sugar in reducing herbicide phytotoxicity or in bringing about selectivity. So let us talk about glucose. Glucose activity. Now, this glucose is produced by glucose is produced by uridine diphosphoglucose. It's one word. Or in short, UDPG. This is so UDGP donates the sugar for the conjugation reactions. Reactions and the enzyme which facilitate the reactions is known as UDPG transferase. Let me rub this. UDP UDP transferase. So this is the enzyme which facilitates conjugation reactions that involve sugar, that involve sugar. So the key points: UDPG will donate the sugar which is used by plants in the conjugation reactions, and they will require the UDP transferase enzyme which facilitates these processes. So the reactions are known as glucosylation. Let me pick the pen. So we're going to talk about glucosylation. This process will require herbicide metabolites carrying the OH, the COOH, and the NH2. So we now have everything: herbicide metabolites, we have got our sugar, which is involved. Now we're going to unpack these three reactions. We will start with the OH one. It is known as the O, glucosylation. Right? What does it involve? It involves the herbicide with an OH plus glucose. Okay, something is happening here. Uh, let me save this. Herbicide selectivity. Sorry for the interruption. So we're saying glucose is produced by uridine diphosphoglucose or DPG. The next issue is the herbicide metabolites. Herbicide metabolites. So these metabolites should carry the following functional groups: the OH, NH2, and COOH. Okay, so let us move on to O glucosylation. O glucosylation. Now you need the herbicide with an OH. On the other hand, you need UDP glucose. So this one we get herbicide or glucose. Right? So what is basically going to happen, UDP glucose will donate the glucose. It will be donated here and UDP is released, whereas the glucose becomes part of the herbicide. And this is all glucosylation, and we need glucose transferase enzyme, or UDP. Actually, it's the UDP transferase enzyme for this activity. I know I had mentioned it earlier on. The other glucosylation of interest is the N-glucosylation. N-glucosylation. This time the herbicide should carry an NH2, and we still have our UDP glucose. This one will produce this is the herbicide. So we have the herbicide, N-glucose. This will donate glucose and leaves as UDP. And we have UDP transferase. Enzyme to catalyze this reaction. Third, we are going to have an ester formation. A glucose ester formation. Let me pick the pen. So we have the glucose ester formation. Now in this case we have the herbicide carrying this COOH herbicide. Again, we still have our UDP glucose. This will produce herbicide, C with a double bond to oxygen, then glucose here. So this is the glucose ester. Glucose ester. Again, this one will donate the glucose and leaves as UDP. You still need the UDP transferase enzyme. Now please remember that for the sugar there are three reactions which take place where sugar will participate in detoxifying the herbicides depending on the radical which is being carried, which can be OH, NH2 or COOH. So this is another way of making the herbicides less toxic. In some plants, these reactions take place very fast and it protects them. Hence, we have herbicide selectivity. Now, the last one is the amino acid conjugation in phase 2, sorry. We will talk of the amino acid conjugation. Amino acid conjugation. Right here, the herbicide should carry a COOH, and we have what is known as aspartate. I won't write the molecular structure of this. So this gives us herbicide NH aspartate. Right. So this reaction will complete phase 3 reactions. So for phase 3, phase 2 reactions, phase 2 reactions key you need to know that these are conjugation reactions. Conjugation reactions and you need to know the role of glutathione. It requires OH or Cl. Then the role of sugar. It requires OH, NH2, then COOH, then aspartate, requires COOH. I think at this juncture we will now move on to the last bit, which is phase 3. Phase 3. Here there is further conjugation. The metabolites from phase 2 are used. We cannot talk about each and every metabolites, but for example, we have glucose, or herbicide, or herbicide or glucose, whichever you want to write it, glucose or herbicide, which is a product of O glycosylation in phase 2. This can be further be altered in phase 3 in this phase. We have what is known as malonyl coenzyme A activity. So basically, we are going to have a malonate plus glucose or herbicide. This will give us a malonyl or malonate glucose, which is joined to herbicide. So when you have this conjugate, it can come part of the cell wall. It can be incorporated into the cell wall. We also have another situation where what are known as chained biocides, chained biocide formation. In this case, we are adding glucose. Then we have glucose or herbicide And this brings us to glucose joined to glucose, joined to oxygen, joined to herbicide. This is no longer toxic. So, final destination of metabolites is going to be cell walls. It could be vacuoles. So please note that herbicide selectivity which is physiological based, it starts with phase 1, then goes to phase 2 and end in phase 3. Now what we are going to do is that we are going to continue with this and show you a bit of details on the slide show. So I will close this. I say that like what we said in phase 2 reactions, please note that these are conjugation reactions. It's like revision now. Glutathione will be attached to the herbicide metabolites derived from phase 1 reactions. The process is catalyzed by glutathione S transferases, if you want to call it in short, GST. The SH of the glutathione is the reacting component. I've actually explained that. Okay. Let me see what is happening here. Right, so glutathione GSH, it is a tripeptide of 3 amino acids, or it is composed of 3 amino acids, glutamate, cysteine, and glycine, or we can represent it using that formula or short form. And you can represent the reaction like that, glutathione conjugation reaction, which requires an OH, and it is that reacting component circled in red, which is going to be joined to the herbicide to form the glutathione conjugate. So glutathione conjugates could be transferred to the vacuole. This is where we have atrazine with the chlorine. Sometimes glutathione can just form a conjugation with atrazine without requiring the OH. Sugar conjugates, we have got herbicide metabolites with the following functional groups. The NH2, COOH, OH. These can be converted to sugar conjugates. We have uridine diphosphoglucose, UDPG, which is the sugar donor. Then UDP glycosyltransferase is the enzyme. We need UDP glucose as the sugar donor. The first reaction is O-glucosylation, where we have the herbicide carrying the OH group will react with the sugar donated by the UDP glucose, and the UDP is released. This is facilitated by glycosyl transferase or UDP glycosyl transferase. This is a typical conjugation of glucose and basagran. We know if we apply basagran to soybean, it's not going to be damaged. What is going to happen is that the glucose within the soybean leaves is going to form some conjugates with the basagran, hence detoxifying it. So here, don't worry about these complex molecular structure. Just worry about the OH and the activity in red. The other process is where you have a herbicide carrying an amine NH2. Again, it combines with the glucose at the nitrogen atom, and the UDP is released. Again, we have the glycosyl transferase. Glucose ester formation, which we have tried to explain. The herbicide should carry the carboxylic acid, the COOH. So you will have UDP glucose donating the glucose. It will become part of the complex structure. Glucose being joined to the carbon to the herbicide plus that oxygen atom. Again, the same enzyme glycosyl transferase. This can also occur to the 2,4-D. You know, 2,4-D has got that portion with COOH. It can be detoxified by sugar, glucose. UDPG donates the glucose, which reacts with the 2,4-D to form a glucose ester of 2,4-D. Amino acid conjugations. We have the herbicide plus aspartate giving us the herbicide joined via the carbon to the NH part of aspartate. Then we have the oxygen there with a double bond, and the herbicide will have been fixed. Again, this can occur with the 2,4-D. It can combine with the aspartate, hence detoxifying it. So you can see that as the herbicide enters the plant, all sorts of reactions can take place. This is probably part of the defensive mechanism of the plant so that it can survive the herbicide attack. But of course, other plants are very susceptible. They may not cope with these reactions, and hence the herbicides will express their mode of action. Phase 3 reactions, plants do not excrete herbicide metabolites, so further conjugation of phase 2 products takes place, moving metabolites into vacuoles for storage, or they can be incorporated into the cell wall. Herbicide glucosides are further processed by the addition of malonic acid residue to the sugar conjugate. So this is what we mean. We may have a malonyl coenzyme A facilitating the reaction where we have a malonate plus glucose or herbicide forming malonyl glucose herbicide complex. This can actually be incorporated in the cell walls, or it can be found in the vacuoles. Then joint biocide formation. This is further glucose conjugations where you have glucose being joined to glucose, then joined to the herbicide. So this would then complete the phase 3 reactions. Here, this is just the summary of all aspects of physiological basis of selectivity. We earlier on talked about cuticular effects, cuticle effects, herbicide movement in the plant, compartmentalization, sequestration. By now probably you should know this. Altered site of action, changes on the structure of the enzyme, where in triazines we have got the changes at the plastoquinone binding site, glyphosate, EP, SPS, allyloxy, phenoxy, carboxylic acids, and the cyclone, hexene, diones, acetyl coenzyme A carboxylase activity, sulfonylurea and imidazolinones, acetolactate synthase. We can write them in short like that. Then we talked about the 3-phase reactions. Phase 1, please note the activity of cytochrome P450 and the formation of functional groups, for example, OH, COOH, NH2, SCH3, SH, and OCH3. Oxidation is important there. Oxidation in itself, it's hydroxylation and dealkylation or dealkylation, oxidative deamination, and sulfoxidation. We also have a reduction of NO2 component, which is one reaction, then hydrolysis, 3 reactions, esters, amides, and nitriles. This summarizes the activities of phase 1. So if we say write about the activities in phase 1, you focus on these reactions. Phase 2, we are looking at the conjugation reactions. All of them are called conjugation reactions, where we have glutathione activity facilitated by glutathione S transferase. Then we move on to glucose activity, which is donated by UDPG, donates glucose or releases glucose. And we have the enzyme again, UDP glycosyl transferase. Herbicides should carry OH, NH2, and COOH. As for aspartate, the amino acid, the herbicide metabolite should carry a COOH. Then the last phase is where we have a malonate, which combines with the glucose herbicide under the influence of malonyl coenzyme A. You get malonate glucose herbicide. Then formation of gentle biocides, where you have glucose being added to glucose. Then we add the herbicide. So this should complete the phase 3. So you can see that the plants are quite equipped at the physiological level of dealing with herbicides. And of course, some plants end up being killed, especially weeds, whereas crops may survive these herbicides. So with this, we come to the end of this lecture. What I will do is to give you 2 questions based on herbicide selectivity. You are going to choose one for your assignment. Thank you.